So we are going to discuss main, you can say, important instructions for paper 5, or you can say uh, what we are supposed to know before starting paper 5. Basically, paper 5 is ATP paper. It's alternative to practical. In AS, you did paper 3, that was the lab, but in A2, you're not going to do the same. We are doing paper 5. The weightage for paper 5 is 10%. There are two questions you will see in paper 5. Each question is of 15 marks. Each question is of 15 marks. Or question 1 would be based on planning and analysis. And question 2 is based upon analysis, conclusion, and calculation. Okay. So we will see that what type of planning we are supposed to have in paper 5 in question number 1, and what type of calculations we are supposed to do in question number 2. But before going to you can say before going to give you this concept, let me tell you few important instructions regarding paper 5. Regarding apparatus, we have different apparatus that we would be dealing with in ATP paper. Like of course, these are the same as you did in your IGCSE in ATP paper or O levels. Obviously, the lab is the same. The apparatus would be the same. Nothing is changed. So the first one is the beaker. The first one is the beaker. So beaker is used for heating purpose, or you can say we can boil water, okay, or we can dissolve something else by using the beaker. But remember, it's not suitable for the chemical reactions. If you are willing to do chemical reactions and you are thinking that I can mix the two substances in the beaker, so it's not good. Why? Beaker has wide opening. It has no close opening, basically, just like conical flask. So in a beaker, may be possible, might be possible that the reaction that you are going to do is an exothermic reaction. Okay. Might be possible that when you would be mixing the two chemicals, so they can splash. Okay. They can splash. Since the beaker has a wide opening, so it would help to splash the liquids, and it can splash onto your face as well. Okay. So that's the reason beakers are not suitable for a chemical reactions. And uh, and it's also inaccurate. It's not recommended that we are supposed to use beaker for measurement purpose. No, it's inaccurate. Okay. And then conical flask, they are suitable for chemical reactions. Okay. Conical flask is just like that. This is a conical flask. Okay. So you can see it has a narrow opening. It has a narrow opening. So once you are going to mix the two substances over here and they are going to react together, and obviously the reaction is exothermic, but the chances of you can say splash of the liquid is minimum in conical flask. Okay. So that's why they are suitable for chemical reactions, especially titration. Okay. And uh, we can also collect gases. If you remember the rate experiments, so we used to collect the gases in this due to its narrow opening, like the minimum chances to escape the gas. That's the reason. Okay. But the tube can be attached for more accuracy. The tube can be attached. Okay. So conical flask are more better than beaker, since we can do chemical reaction. But obviously, different apparatus have their own uses, basically, you can say. And then we have volumetric flask, which is used for making solutions, especially. They are purpose built, you can say, apparatus. in which we can prepare the solution. Exact amount of solution we can prepare. Let's suppose you are saying that you're asking that I need 25 centimeter cube of solution and the concentration should be zero point 0.1 mole per decimeter cube. I would be telling you that how can we prepare a solution by using the volumetric flask. You know, this is the this is the volumetric flask. This is the volumetric flask. And interestingly, there is no any graduation on the volumetric flask. Only you will see the one mark over there, okay? And it comes in different sizes. You can see the 10 cm cube volumetric flask. You can see the 20 cm cube volumetric flask. You can see the 50 centimeter cube volumetric flask. Okay. Uh, so, so of course, to prepare exact amount of solution, we can use volumetric flask. Okay. They are more accurate. They are more accurate basically. Okay. Or let's suppose I'm saying that you have to prepare you have to prepare 250 cm cube of you have to prepare listen very carefully. You have to prepare 250 cm cube of HCl solution HCl solution having zero point 0.1 mole per dm cube concentration. Okay, zero point 0.1 mole per dm cube concentration, right? Okay, so the first thing is that obviously how much sample should I take from the stock and then add water to make this concentration. So first of all, you have to calculate the mass of the substance that you are supposed to take, and then you are supposed to weigh it through weighing balance, and then you are supposed to pour the sample into the volumetric flask and then add water and then add water, okay, to make this concentration. Let's suppose this is not HCl, this is, to make it simple, this is sodium carbonate. This is what? This is sodium carbonate. Na2CO3. This is sodium carbonate, okay? Uh, First of all, I would be calculating the mole of sodium carbonate. Mole is equal to the concentration times volume. Concentration is zero point 0.1 times 250 centimeter cube divided by 1000. Okay, unit must be the same. If this is dm cube, so it should be dm cube. So that's why 1 dm cube is equal to 1 dm cube is equal to 1000 centimeter cube. Okay, so I would be dividing this by 1000. I would be multiplying this. So I would be getting the moles of sodium carbonate. Okay, can you tell me the answer? Yes.
Zero point zero two five.
Your voice is not clear.
Sir, it's 0.025.
0.025 mole of sodium carbonate. Then I need the mass. So mass of sodium carbonate would be equal to Mr. Moles. Would be equal to Mr. Moles. What is the molecular mass of sodium carbonate? Hmm. Hmm. Yeah. Yes. Fast. Hmm. What's the molecular mass of sodium carbonate?
50.
106.
106 multiplied by the moles, that was 0.025. So it would give you the grams of sodium carbonate. It would give you the grams of sodium carbonate basically, right? Grams of sodium carbonate. Yeah, what's the answer? Hmm.
2.65.
2.65.
2.65 grams. So what you are supposed to do, just go to the weighing balance and almost you have the stock of sodium carbonate solid. Okay. Take 2.65 grams of sodium carbonate. Okay. Or I can say weigh 2.65 grams of sodium carbonate. Weigh 2.65 grams of sodium carbonate and add to 250 centimeter cube volumetric flask. 250 centimeter cube volumetric flask. Okay. Let's suppose this is the 250 centimeter cube volumetric flask. Okay. Right. I have added this much grams of sodium carbonate and add water. This is the mark till 250 cm cube. This is the mark till 250 centimeter cube. Okay. And add water to make up the solution. To to make up the solution to automatically you would be getting this concentration automatically. Once you have added 2.65 grams of sodium carbonate in this volumetric flask and then keep adding water until it reaches over there. Okay, it's full of water. Like we generally say that make up the solution to 250 centimeter cube. So then you have prepared zero point 0.1 mole per dm cube concentration solution of sodium carbonate. It's for solid. It's for solid. If you have solid, so in this way you can prepare the desired concentration. Now you can see we are going to prepare the solution in a volumetric flask. Okay, this is more accurate. This is much accurate. So that's the reason whenever we are going to prepare solution, so we are supposed to take volumetric flask. What if, what if I want to dilute a solution? What if I want to dilute a solution? Let's suppose you are doing your experiment and you need 2.0 mole per dm cube concentration of HCl, and you are 50 students, so let's suppose you are saying that we will consume approximately 500 centimeter cube. So we need this much volume of HCl and the concentration should be 2 mole per dm cube HCl. And then I'm in the lab. I know that when I have purchased HCl, so the concentration was 13.0 mole per dm cube. It's highly concentrated. It's highly concentrated. Of course, I would be taking few centimeter cube of this much HCl solution, and of course I would be adding some amount of water. Then after the addition, Then after the addition, automatically I would see when I would be making up the solution. So automatically I would be getting the same concentration. But the thing is that how much volume should I take 13 mole per dm cube HCl solution to make this much dm cube of HCl solution, and the volume is 500 centimeter cube. So we are supposed to use this relation, that is C1V1 is equal to C2V2. Okay. C1V1 is equal to C2V2. Okay. So this is for this is for this is for this. Okay. Right. And this is for this. Okay. So I need the volume of 13 mole per dm cube concentration to make up the solution of 500 centimeter cube having the concentration of 2.0. So the volume would be equal to 2 into 500 divided by 13.0. Can you tell me an answer? Yes. And you are supposed to convert the volume into the obviously dm cube. Okay. You are supposed to convert the volume into the decimeter cube, of course. Yeah. What's the answer? Mhm. What's the answer?
Size 77 centimeter cube.
So it's 77 centimeter cube, okay, of HCl. Now you went to the stock solution in your cupboard. You have just taken this much concentration of HCl, and then just you took away 77 centimeter cube, okay, from this stock solution, and then you have added, see this, and then you have added 77 centimeter cube of HCl. Then you have added 77 cm cube of HCl into the same volumetric flask, and then add distilled water, up to the mark, and then add distilled water up to the mark over here. Automatically you have prepared your 2 mole per decimeter cube solution. In this way, you can prepare the solution from the solid as well, from the liquid as well. If you have solid, so obviously you have to use weighing balance. And if you have liquid, so of course you have concentrated stock, then just you are supposed to take few mLs of the stock solution and then add into the volumetric flask and then add water up to the mark. Then automatically you would be getting your desired concentration. Okay, that's the method that we would be dealing with, inshallah, when we would be doing the past papers. But before going to do again, uh, we have other things as well. That is, I was telling you that uh, volumetric flask. Okay, then we have burette as well. Okay, burette is also the accurate one. Basically, burette has a larger in size. You know, it's of 50 centimeter cube. You can have 50 centimeter cube of liquid in a burette. Burette is also accurate. Then we have pipette. Pipette is also accurate. Okay, pipette is also accurate. Um, but beaker and conical flask, they are not accurate. Beaker and conical flask, they are not accurate. Okay, these are common laboratory apparatus. Then let's suppose if I want to heat the substance, something that we are going to use in a lab, and it's going to release carbon dioxide gas. Let's suppose calcium carbonate. So first of all, you have to decompose this calcium carbonate by heating. So the thing is that what apparatus I am supposed to use for heating. So there are two types of heating. The first one is strong heating and another one is the mild heating. For strong heating, you can use Bunsen burner, but for a mild heating, you can use water bath or electrical heater that are thermostatically controlled. Okay. Um, let's suppose Bunsen burner, generally used for strong heating, for the decomposition of any substance, for boiling purposes, because they provide strong heating. Okay. But the thing is that the Bunsen burner is not supposed to use for the heating to flammable substances because they catch fire. If you have a naked flame, the open flame, and you are going to use organic solvents, so of course your solvent can catch fire through the open flame, through the naked flame basically. So that's the disadvantage, okay? And also the flame is not evenly distributed. The flame is not evenly distributed. You know why I'm saying this? Let's suppose you have a beaker. Let's suppose you have a beaker and you want to provide heat. Let's suppose this is the beaker and this is the Bunsen burner flame and this is a liquid in it. So if you are going to provide heat, so only this portion would be having a higher temperature. Rest of the area would be cooler comparatively. That's why I'm saying that your Bunsen burner is not going to provide you a even distribution of heat. Okay. So that's the reason it's not uh, accurate, I can say. Second thing is that we generally use a wire gauze. We generally use a wire gauze. Wire gauze is used to distribute the flame. If you remember the wire gauze, let me tell you this. This is your wire gauze basically, okay? This is your wire gauze. See this? This is your wire gauze. So once you are going to provide heating to any of the beaker, to any of the apparatus, okay? So you are supposed to put the wire gauze, okay, onto the flame and then start to provide heat. So what the wire gauze would do, your flame would be evenly distributed. So then you will see the 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 beaker that contains the sample. Let's suppose the sample is water. It would be having even you can say heating environment. Okay, and sometimes we provide gentle heating. In some reactions, the gentle heating is required, like in crystallization. If you are going to provide strong heating, so your crystal would decompose, your crystal would break down. Okay, but I need crystals. I'm not supposed to provide strong heating. I need gentle heating. So for a gentle heating, we generally use electric bath. We generally use water bath. Remember, okay. So what they do, they provide they provide uniform heating. They provide uniform heating. Okay. So then, of course, how to prevent heat loss? Let's suppose I'm going to provide heating to anything, to any reaction, to any chemical. Okay. And after providing heat, we are supposed to measure the enthalpy change. But I'm hoping that the heat is not lost from the system. That is the reaction that is taking place in a beaker or any of the volumetric flask. So you're supposed to have proper insulation material. The beaker, the container in which you are going to do a chemical reaction, especially for those reactions in which you are going to measure the enthalpy change. So you can use a styrofoam cup or you can put a lid on over there and take readings quickly. These are few steps by which you can minimize the heat loss. I'm not saying that you can you can prevent heat loss 100%. No, it's not true. You might have some heat loss, but the thing is that we can have the minimum heat loss by doing these steps. You can take a styrofoam cup, which has a proper insulation material. Okay. So 100% that the heat that you have provided into the system, so you can measure it. You can measure the enthalpy change accurately, almost near to the true value. Okay. So the higher the temperature, so the higher the heat loss. The higher the temperature, the higher the heat loss. So probability of the heat loss is higher if you are going to provide a higher temperature. And if you're dealing with those reactions in which there is a lower temperature, so the probability of heat loss is lower. Okay. And what are the methods by which we can cool the gas? Uh, Sometimes we need vapors. Vapors means a gas in the form of liquid, basically, right? Like water vapors. When the vapors condenses, when the vapor condenses, so they would give you a proper liquid. But how can I condense the vapor? Whether the vapor is of water, whether the vapor is of any of the gas. Of course, the gases have a greater kinetic energy. Okay, they are going to move randomly, they are going to move faster. And after decreasing the temperature, after decreasing the temperature, you can decrease the activation energy of the particles. You can decrease the activation energy of the gas molecules, of the gas atoms. But how can we do this? As you can see, the gas is going to pass through this U tube, just like that, and is going to enter into this environment. This is your crushed ice. Of course, it's helping to maintain the temperature of this U-shaped tube. And when the gas is going to enter into this U tube, so of course it would meet the colder environment. Automatically, the particles would be losing their kinetic energy due to the lower temperature. And you will see due to the lower temperature, the kinetic energy would be lower. So now they will be, you can say, their temperature would be lower. So I can say that the gas is cooled. In this way, you can cool the gas. Another way to cool gas is to use a Liebig condenser. It's a very famous instrument if you have ever seen this in your previous classes. It's a condenser in which we are supposed to enter water from the lower side, and this is your water out. Okay. Why we are doing this? Why we are doing this? We are going to reduce the temperature of this tube so that when the gas is going to enter into this tube, just like that, so the temperature of the gas would be lower, would be decreasing, okay, would be decreasing, and ultimately you can see the gas is going to convert into the liquid form. Okay, the gas is going to convert into the liquid form. So, so we have the two ways. Number one, this, okay, and number two is this. Okay, we have two ways, right? Uh, then how can we collect the gas? These are the things, these are the things that you will meet when you are solving the paper 5. Okay. Number one, you can collect the gas through the gas syringe. Okay. You can collect the gas over water, but few of the points that you need to keep in mind that the gas should not be soluble in water. Otherwise, this method would fail. Okay. So by this method, you can only collect the gas which are insoluble in water. You can see the bubbles. You can see the bubbles. And this empty area is your collected gas. This empty area is your collected gas. Okay. Then we can use these two methods that are upward delivery and downward delivery. When the gas is heavier than air, so you can collect the gas through the downward delivery. And when the gas is lighter than air, so you can use upward delivery. Okay, these are the methods by which we can collect the different gases. And then how can we dry a gas? How can we dry a gas? Okay, so we have to use a drying agent. We have to use drying agent that are anhydrous calcium chloride and concentrated sulfuric acid. Okay, anhydrous calcium chloride and concentrated sulfuric acid. Let's suppose in this diagram we are going to pass moist HCl. Moist means HCl plus water. Okay, and once it's going to enter into the concentrated sulfuric acid, it would absorb it would absorb the water content. It would absorb the water content from the gas, from HCl. And afterwards, when it's leaving the beaker, when it's leaving the container, when it's leaving the container, so now it's the dry HCl. So of course, your concentrated HCl has absorbed water. Your concentrated HCl has absorbed water. Okay. Now, then we have this method. We have fused calcium chloride powder over there. I'm going to pass the moist hydrogen gas. Okay, the wet gas. Once it's going to enter into this environment containing the fused calcium chloride, so I would see that all of the water content have been absorbed by this anhydrous calcium chloride. And when it's leaving the container, when it's leaving the beaker, you will see that you would be having dry hydrogen gas, that you would be having dry hydrogen gas. Okay. Okay. And then this is very important criteria of the paper 5 that you would be drawing a graph frequently. So the question is that how can we draw the graph? And before going to draw the graph, what what are the points that we should keep in mind to draw any of the curve, to any of the straight line, means in general to draw any of the graph. So before going to do this, we need to know these two variables. The first one is called independent variable and the second one is called dependent variable. What is independent variable? That we can change, we can control it during the experiment, during the experiment. So dependent variable changes, changes, changes as independent, as independent changes. In short, dependent variable is depending upon this variable. If this is going to be changed, so it would change automatically. Let's suppose if you remember the rate experiment, we used to find the factors, we used to find the factors on which the rate depends. We had some factors that was concentration and pressure and temperature. Okay, these are the factors. So let's suppose if you are going to double the concentration, so concentration is the factor that is in your hand. Concentration is the factor that is in your hand. You can change the concentration. You can increase the concentration. You can decrease the concentration. That's in your hand. As you're going to control it, it's called independent variable. And what's the dependent variable? It depends on concentration. As the concentration changes, so the rate changes. If you have doubled the concentration, so the rate would be doubled. If you have half the concentration, so the rate would be half. Okay. So means that the rate of reaction is the dependent variable that is depending upon concentration. And always remember the independent variable should be kept on x-axis, and the dependent variable should be on the y-axis. It's mandatory because sometimes the examiner would be giving you the question and he wouldn't be mentioning that like which species is going to put on which axis. You have to decide by yourself. Okay. So of course, by looking at the reaction, by reading all the mandatory explanations, all the important instructions, that we would decide, okay, which one is your dependent variable and which one is your independent variable. So then after knowing the dependent and independent variable, we would be able to put the correct thing on the correct axis. That's the main point. Okay. Or or then, you know let's suppose um, planning to I am planning to study how the rate changes as the concentration changes. So of course I am quite interested in changing the concentration, and I would study the effect of changing concentration on the rate. So the rest of the factors should remain constant. So the rest of the factors should remain constant. So the rest of the factors are pressure, temperature, surface area. Because if you are going to change all the factors, so how can you study the effect of concentration on the rate? Because other factors are also changing. Okay. So to study the factor of like to study the effect of concentration on rate, you are supposed to keep other factors constant. Okay. So these other factors are called controlled variable. These other factors are called controlled variable. Hmm? Okay. Then you will come across with the two types of lines in your graph. The first one is a straight line, and the next one is the curved line. If you're going to deal with straight line, and examiner would be giving you the different points that you have to plot by yourself. Okay. And then you have to look, okay, the examiner is saying that you have to draw the best fit line. It's a misconception. Most of the students think that line of best fit is a simple straight line that joins first point to the last point. No, it's not true. That only you have took your ruler and then you have put your ruler on the first point and then you are going to just make a straight line to the end point. No, it's not true. So never join from individual and like initial and final. No, 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 no. Rather than this, you have to see what are the points that you have plotted. Equal scattering. You are supposed to do equal scattering of all the points below and above the line. Just like that. You can see that there are two lines. The first line is correct line of best fit, and another line is incorrect line of best fit. So the correct line of best fit consists above, then on, then below, then above, then on. Like it's a uniform scattering. It's a uniform scattering of the points. Okay. It's a uniform scattering of the points, right? So this is very important thing that you need to keeping in mind before drawing the graph. Then you can see that in some experiments, you will see the anomalous points that are called outlier. Like these points are out of the way of your experiment. You were not expecting this point, but of course, due to some error, due to something, you got this point. That is called outlier. We will study. It depends on case to case that what we are doing in the question, what type of experiment is going on in a specific question. Okay, so we will do this, and then again, this is the best fit line. Okay, so when you will be drawing the points by yourself, and then when you would be drawing the line, then you will be able to know, okay, what we are supposed to do when we have these type of points. So to make it more clear, I have some paper in which the examiner has given us some points, okay, and they're asking to draw uh, the best fit line. Okay, so let me show you the same question. So as you can see, this is the paper. It's Feb March paper 52 2023. They have given you some points and provided you x's, x and y axis. It's a graph log up 1 over t versus log v versus log v. First of all, you have to find the values of log v and log 1 over t. So you are supposed to tell me the answers. You are supposed to tell me the answers, then I would be solving this, right? Okay. Uh, Let me open the paper first. Let me open the paper first. Then I would be solving it. Okay. So that you can understand in a better way. Uh, yes. Can you tell me log V? This is your V. Just take a log and tell me your answer fast. Yeah. Mhm, mhm. Jaldi, jaldi. Mhm, mhm, mhm. Yeah. Fast.
Zero point 0.699.
First one is 0.99. Okay.
699.
0.699. And what is log 1 over t?
Sir, it's negative 2.4.
It's negative 2.2. Okay. Then negative 2.2 or 2.41.
2.4. 2.4.
2.41.
Yeah. Then experiment 2. Log 10 is 1, of course. Yeah. What about log 1 over t?
Negative 2.08.
Yeah. Next. Mhm, mhm. Next point. Yeah.
1.096.
1.096.
Yeah.
It's almost 1.1, right? 0.9 is 1. Okay. Okay. Then next. Mhm.
Negative 2.049.
Okay. Then next.
1.176.
Approximately 1.18. Okay. Next. Mhm.
negative 1.83.
Negative 1.8.
8,
Okay, then 6 and 7.
1.30,
Okay, next.
negative 1.75,
Okay,
one point three nine seven,
1 point.
397.
No, no. Log of 25.
Yes, so I'm getting 1.397. So 1.40.
1.40 is this, right?
Yes,
And what is this? Negative?
negative 1.64.
Okay. So now you are supposed to draw all the points. And one thing that it is recommended that you're not supposed to put dot, 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 dot. This is wrong method. Rather than you are supposed to use cross. You are supposed to use cross. Okay, you are supposed to use cross. It's more accurate. Cross is more accurate. Uh-huh. The first point is on 0.699. The first point is 0.699. Okay, log V. So 0.699 is where? Yeah, 0.699. This is 0.7. This is 0.9. This is 1.1. This is 1.30, if I'm not wrong. Hmm? Okay. So, so what was the point? 0.699. Of course, it's 0.7. And what is the log 1 over t value? Negative 2.41. So I got the first point. I got the first point. Okay. I got the first point. Set. Then the next point. Negative 2.08 and then 1. 1 is this. 1 is this and negative 2.08. Negative 2.08. So let me describe other points. Let me describe other points. If this is 2.60, so this would be 2.40. If this is 2.40, then this would be negative 2.30. Okay. And this would be 2.10. This would be negative 1.70. No, it's not 70, it's 90. Then it would be 1.70. Okay. So what was the next point? 2.08 and 1. 2.08, 1. 1 is this. 1 is this. Okay. 1 is this. And this is 2.10. This is 2.10. They're asking 2.08. So 2.10 and 1, that would be 2.08. Okay. Set. Then negative 2.05 and 1.10. So this is 1.10 and negative 2.05. Negative 2.05. 1.10. 1.10 is this. 1.10 is this. Then negative 2.05. Yeah, 2.05. So this is 2.2, then 2.1, then it would be 2. Okay. So this would be 2.05. What do you think? Should be over there? No, it's at 1.10. Okay, okay, okay. Just like that. Okay. Then we have 1.18 and negative 1.88. 1.8, 1.18, 1.18 and negative 0.88. So 1.18 is this, just over there, 1.18. Okay, 1.18 is this. And what? Negative, negative 1.88. Around, around, around here. Okay, then, then we have 1.30 and 1.75. This is 1.30. This is 1.30 and 1.75 is just like 1.75 is just like here. Okay, true. Then the last point we have 1.40 and 1.64. This is 1.40 and this is 1.64 is over there. Okay, I got the points. I got the points. Okay. So at 1.30, what it was 1.30 per 1.75, Tana. 7.75 is not like that. 75 is this. Oh, okay. Now you have to now you have to draw the best fit line. What the examiner is saying, draw a line of best fit. Draw a line of best fit. Just you are supposed to take the ruler. Just you are supposed to take the ruler just like that. Okay. And
Sir,
then yeah,
how is that point 1.75? Shouldn't it be like down?
it's 1.75, 1.8 and 1.75, then 1 point. Oh yeah, exactly. It should be the number is going to decrease, right? 1.8, then 1.7, then 1.6. Around here, if I'm not wrong. Yes or no?
Yes, sir.
Okay. Now I'm going to take a ruler. Then I would be drawing a line of best fit. So I can draw the line of best fit. Is this good? Is this good or bad? I'm supposed to try this. Yeah. Okay, this is the line of best fit basically. Okay, so this is your outlier. This is your outlier. Let me check this point. Why this point is not on the main line? Let me check this point again. I'm talking about I'm talking about 1.00. So 1.00 was negative 2.08. 2.08 2.08 would be like that. I did wrong. It's 2.08. Okay. In this way, you can draw your curve. In this way, you can draw your curve. Okay. It's a line of best fit. Now they are saying, give the gradient to two decimal places to calculate to calculate the gradient. Okay. So I'm taking the points. I'm taking the points. I'm drawing the triangle. I'm drawing the triangle. Okay. I'm drawing the triangle just like that. This is the point that is y1, y2. This is my x1. This is my x1 and this is my x2. X2 is this, x1 is this, y1 is this, and y2 is just over there. So y2 minus y1. Y2 is y2 is it's just over there. Negative 1.60. Y1 is negative 2.40 over x2 minus x1. X2 is 1.4, x1 is 0.7. Then you would be getting your desired answer. Okay. So in this way, we can draw the curve. In this way, we can draw a best fit line and we can calculate the gradient. Inshallah, we will be doing the more questions on it. But of course, we have to go through how to find the percentage uncertainty of different apparatus, and we have to go through some other things as well. Okay, how to find out the anomalous point and why we got anomalous point. These are the main questions that we need to go through. Okay, so inshallah we would be completing this.